Alright, we are at topic 8, introductory organic chemistry. So I will briefly run through some of the main points as usual. Okay, but maybe before I run through this, you might want to take a look at the earlier video on the bridging organic chemistry course if you are not sure about some of the functional group which you should have learned in secondary school, or if you need some recall. Okay, so there are also some SLS resources available on on SLS. I think they are indicated in the lecture learning plan. So if you wish to, you may also refer to them. Okay, so without further ado, I just want to highlight that organic chemistry is a huge topic. I think by and large it covers around 1/3 to about 40% of the chemistry curriculum you're going to experience in H2. Yeah, so of course it's of vital importance for you to understand the content well, and not to memorize the things unnecessarily. Okay, so just going to share with you a little bit about maybe some of the learning outcomes. I'm not going to go into details, but I want to draw to your attention the learning outcome 11.1c. This is actually very important. At this stage, it may not be of any importance to you. I think the point I'm trying to say is that even after you have learned this particular topic, you might not really understand a lot of the terminology which they indicated here. So, for example, delocalization, electronic effect in terms of electron donating and electron withdrawing effects, and as well as steric effect, or otherwise known as steric hindrance. But please keep this learning objective 11.1c at the back of your mind when you're learning organic chemistry, because every topic in organic chemistry, every functional group, inevitably you will be exposed to these three terms, either all at once or maybe two out of the three terms. So maybe I can just stress that at this stage, after learning this topic for the 27 pages, if you don't understand these three terms, it's perfectly fine. It doesn't really matter because it wouldn't affect your learning at all at this stage. Okay, just keep them at the back of your mind, and if you keep looking back, exposing yourself to these terms using the correct functional group, seriously, there isn't really a lot of points in going into deep details now, but yeah, when you are exposed to them, you look at the terms, you read the terms, you read the explanation, then it will make a lot more meaning to you. So to understand objective 11.1c, is easier to connect the dots backwards rather than forwards. Okay, 11.1d in Hua Chong, we have covered them under chemical bonding, so that should be relatively straightforward. 11.1e, in terms of hybridization theory and what exactly is a sigma and pi bond, I think you would have been exposed to them. So I don't think it's of any difficulty. So if there's anything I need to highlight to you, I will bring to your attention when we reach there. Okay, understanding reaction mechanism. You are exposed to reaction mechanism in kinetics. Okay, however, over in organic chemistry, we represent mechanism using a slightly different way. Yeah, we use arrows, or in particular curly arrows, okay, that look something like this. Curly arrows to represent electron pair movement, or we use a fish hook like this to represent a single electron transfer. Yeah, so you need to get used to how to draw these arrows when the time comes, especially when you are required to learn the 5 mechanisms in your H2 curriculum. Okay, and of course for 11.1h, I hope it's not new to you. because you are supposed to recognize that the mechanism of polar reaction involves the flow of electrons from electron rich to electron deficient sites. Why do I say that this is not new to most of you? The reason is because if you heard me explain to you in the early days, let's say in late term 1 or early term 2, right? I use a very simple example to explain acid-base neutralization, especially when we are looking at energetics. I was sharing with you that OH minus, okay, with an electron rich site at the oxygen, that's what we call the lone pairs, is what we call a Lewis base. Okay, so I think even in our blog test review, I highlighted to all of you that we call this the Lewis basic site. And then of course H plus, being electron deficient, we call this a Lewis acid. Okay, and you know that when they react, they form a new bond. So I'm going to represent this bond in red. Yeah, so this is what we call the OH sigma bond being formed when the Lewis base reacts with the Lewis acid. Okay, so for the purpose of H2, when we talk about electron, the flow of electron pair, all we need to do is we need to start the electron pair movement from the lone pair, and then we draw a curly arrow and point towards the H, and then put in the arrowhead. Yeah, so this is known as electron pair movement. So we are simply saying that, you know, the lone pairs of electrons attack the electron deficient H plus. Yeah, such electron pair movement is quite common in organic chemistry and in terms of representation. I mean, we are not really saying that the electron moved, you know. We are just saying that we are using this as a form of representation for organic chemistry. This actually helps organic chemists to be able to better visualize where where the bonds are being formed and broken. Okay, it is largely for the ease of visualization. It's not meant to say that, you know, electrons are really moved that way. Okay, so I think this is quite important for all of you to recognize that. Yep, so I'm going to move on. Okay, so I'm not going to go into details the introduction. I think I have gave quite a bit of introduction already. So I'm just going to move on to the next part. So there are different classes of organic compounds. Of course, we give you a whole list on the next page, but maybe by and large you want to know three terminology over here, so so that it's clear what so that we are on the same page when we are doing discussion. So the first terminology is aliphatic. Aliphatic means it can mean straight chain, it can mean branch. So basically just any compounds without any rings lah. So we call them aliphatic. Yeah. So there's another term known as alicyclic. Okay, actually aliphatic and alicyclic, some people can put them in the same category. So that means that in the compound there's a ring system, but the ring system is not aromatic. So aromatic represent a special kind of ring system where if you look at it, it obeys Harker's rule, but Harker's rule is not in your H2 curriculum. So most of the aromatic system you encounter in H2 benzene ring with 6 pi electron. Okay, so if you do a quick count, there are 6 pi electron in total. Yes, so if an aliphatic or alicyclic compounds contain only single bonds, we term them as saturated. Saturated meaning it doesn't have any pi bonds. Okay, so only single bonds. Yeah, so any system with pi bonds, etc., we give them a special name, we call them unsaturated. Yeah, so that's about it. And for the functional group, you'll be a bit shocked because there are a lot of them written here. So again, maybe I can stress that do not be alarmed or do not attempt to memorize them. Yeah, so really I really mean what I said. Don't attempt to memorize any of these functional groups at this stage. I mean, if you want to, if you really wish to, you might just want to focus on the hydrocarbons. Yeah, because they are going to be tested for your promos anyway, so they are just alkane and alkene. Okay, arenes will not be tested in your promos, but arenes you'll be taught arenes before promos as well. So I mean, it will be good for you to know what are arenes. As for the rest, I think my point is just recognize them as and when just return to this page as and when you look at some functional group, and then they are of interest to you. Okay, or you can easily look at a textbook or run a Google check. Okay, so I will not attempt to go into like nitty-gritty details on what's the difference between a carbonyl compound and maybe a carboxylic acid, and what are carboxylic acid derivative. Yeah, so when the time comes, then we'll deal with them. I think that's really easier. Okay, I think you heard me mentioning this term in the bridging module, homologous series. So basically, the difference between successive members in a homologous series, they differ by a CH2 units. Okay, so if you recall from the bridging course, I was telling all of you that these are the terms you need to know at least for the first small member: meth, F, prop, and built. Yeah, so the rest will follow the usual kind of numbering which you are familiar with from English. So pence means 5, hex means 6. Yeah, it is the first 4 members that require some attention, and maybe you might want to commit them to your memory so that you really understand, you really remember that you don't get mixed up with between ethane and propane and butane, etc. Okay, yep. The degree of substitution is relatively important in the context of organic chemistry. So especially this particular term, primary, secondary, tertiary, and quaternary. Yeah. So maybe I'll just use one example to highlight to you. So for example, for alcohols, okay, you classify them as primary, secondary, or tertiary. There are 2 perspectives which you can look at. So the first perspective to look at is to determine whether is it a primary alcohol. We look at the number of R groups. So if we have one R group here, well, okay, you might be wondering what are R groups. R groups are any LQ groups. So normally we just term them as R. So it's just some random straight chain or branch chain LQ. Okay, it could also be a ring, not a problem at all. Okay, it could be aliphatic or alicyclic. Doesn't really matter. Okay, so if you have one R group, we call it primary. 2 R groups, we call it secondary. I think it matches. And then 3 R group, we call it tertiary. So there's a shorthand, there's a short form way of writing. So primary, we can write it as 1 degree, but please do not pronounce it as 1 degree. Let me repeat. Do not pronounce it as 1 degree. Okay, it's called primary. Okay, secondary and tertiary. Okay, it's the same as halogenal alkane. So if you have 1 R group, it's primary, 2 R groups, secondary, 3 R groups, tertiary. So it matches really well. And then if you write it out, then it will be primary, secondary, tertiary. Yeah, you might be asking if there's another perspective of looking at it. Yes, there is another perspective if you wish to. So another perspective, let me just erase this. Another perspective to look at things would be, instead of counting the number of R groups, right, we can count the number of H. So if there are 2 H, then it's primary, 1 H secondary, no H tertiary. Yeah, so that's fine as well. So 2 H primary, 1 H secondary, no H tertiary. Yep. Okay. For quaternary with 4 bonds, with 4 so-called R groups, usually it is only possible for quaternary ammonium salts like this. Yeah, the reason why you can't have quaternary for other functional group is because for each carbon, if I already take up a functional group, I call it Fg, right? So the maximum number of R group you can have is 3. Yeah, so tertiary it will be the maximum. But if let's say it's a amine based compound with N in between, then I could have more than 3 R groups. So we call this the quaternary ammonium salt. Yep. Okay, so without further ado, we can quickly look at example 2.1. So you have an antibiotic drug. So you are asked to circle and name the functional group present. So you can always refer to this particular page. I think this is page 4. So just refer to them. Okay, as you do this part of the question. So I'll just quickly solve it for you. So we have a benzene ring over here. So you might want to take note of it. So this is a benzene ring. Okay. Yeah, so we have a benzene ring over here. Yeah, or you can call this compound an arene as well. Okay, but you might want to take note that benzene ring may not be the best way to call this particular 6-member aromatic ring, which is part of the molecule. The reason is, strictly speaking, benzene has the formula C6H6. Yeah, so when benzene contains substituent, a better way to call it will be phenyl, P-H-E-N-Y-L. Yeah, so calling it phenyl ring is actually a more accurate representation. But you will probably hear a lot of people say benzene ring. Okay, I mean that's fine colloquially lah, but phenyl ring is actually a better way of calling it. Okay, so next we have a nitro group here. So this is a nitro. Yep, this functional group you don't really learn it in H2 except of its electron withdrawing effect. So again, I introduce you another term, electron withdrawing effect, which we will talk about it later on. Okay, and then so over here you notice this interesting functional group you might have seen before in secondary school. So over here, so this is called amides. Okay, so this is called amides. Okay, and if you recall earlier on about this primary halogenal alkane, okay, so indeed it is present here. Yeah, so we call this a primary chloroalkane. Okay, yep, and of course not to forget our good friend here. We have an alcohol here, and then another alcohol here. Okay, so again, I leave it up to you. If you want to count the H, it's fine. So if you count, there are 2 H's here, so this will be called a primary alcohol. And then this has only 1 H, so we call this a secondary alcohol. Okay. Some of you might be a little bit confused about one of the terms, so maybe I just go back to this. Let's say for an alcohol, okay, you might be a little bit confused over, for example, the usage of the term hydroxyl as well as alcohol. Oh, sorry. Yeah, as well as alcohol. Okay. Maybe without going into very big details, which I don't think I should because it's really not so crucial for H2, but I thought I can just give you a bit of explanation. It will be on the difference between a functional group, okay, and simply a group. Okay, so a functional group is clearly defined by what we have here. So, like for example, these are the names which we clearly define those groups. Like if it's a ketone, it's called ketone. If it's a carboxylic acid, it's carboxylic acid. So these are, I mean, it has some historical origin. Yeah. So in that case, for example, we call this a carboxylic acid. So this is known as a carboxylic acid. But we do not call this a hydroxyl. Yeah. So in that sense, you can tell from here maybe that this CO as well as this OH, right? They are better known as groups. So which means a carboxylic acid is made up of a carbonyl group, okay, and a hydroxyl group. Yep. So that means that if I ask you to name this compound, you cannot name it as a carbonyl and hydroxyl. Or rather, if I ask you to give the functional group present in, let's say, this compound, CH3CO2H, you cannot call it a carbonyl and hydroxyl. You have to call it a carboxylic acid. Yeah, because the functional group is carboxylic acid. Yeah, you do not mix the group up with the functional group. Yeah, so of course, occasionally, for some compounds such as alcohol, right? Yeah, the functional group and the group are the same thing, which is OH. Yeah, so that's fine. Yeah, so it might be better for you to learn how to distinguish them. If you have not learned how to distinguish them at this stage, I think it's fine also. I shouldn't put too much pressure on yourself. Yeah, just take it as it comes. I think it should be it. I mean, over time, you should have a much clearer picture. Okay, okay. Next, we're going to move on to discuss the type of molecular formula. Yeah, so I thought for the type of molecular formula, it's easier if I use ChemDraw to explain. Okay, so for the type of molecular formula, the first type is something which you might be relatively familiar with, is what we call the molecular formula. So let's say if I just give you a simple compound, let's say what should I give you? Let's say ethane dioic acid, ethane dioic acid, or the common term is called oxalic acid. So let's say I use ethane dioic acid as an example. Okay, so for ethane dioic acid, the molecular formula will be C2H4O2. So this is known as the molecular formula. Oh, sorry, it shouldn't be. Sorry, it's C2H2O4. Okay, yeah. So we call this the molecular formula. Yeah. So what does a molecular formula mean? So a molecular formula basically showcase the exact number of the different types of atoms that is present in uh, ethane dioic acid. Yeah, so it represents the exact number, and you notice that um, each atom only appear once, or each unique element only appear once. Yeah, okay, so that's something you need to remember. And of course, you learn this in secondary school as well. The next formula, which you might be familiar with, is what we call the empirical formula. So the empirical formula for ethane dioic acid is CHO2. So we call this the empirical formula. Yeah. So basically, the empirical formula gives you the lowest ratio between the elements. So for example, ethane dioic acid molecular formula is C2H2O4, so it's 2:4 ratio. So for empirical formula, it will be 1:2. You also notice that from the molecular formula and empirical formula, in most cases, it is almost impossible for you to come up with the structure of the unknown unless you have some background of it, or unless other information were provided to you. So actually, these two formulas on their own, they are not very useful for you to draw out the compound, okay, because they don't give you any other details. Yeah, but they are important for the purpose of for definitions. Okay, then another kind of formula which you are very familiar with since secondary school is what we call the displayed formula. So the displayed formula is when you actually showcase all the bonds that could be present in your unknowns. So in our case here, for ethane dioic acid, I have the O here, the carboxylic acid, okay, and then a H, and then two carbons. Yeah, so this is what we call the displayed formula. Yeah, so this is the displayed formula. Yeah, so you notice that for displayed formula, right, all the bonds are shown, which means all the different types of connectivities are clearly indicated in the displayed formula. So there's no ambiguity. Yeah, so if it's a double bond, it's a double bond. If it's a single bond, it's a single bond. So there's no ambiguity here. Yeah. Okay, so a displayed formula, I mean, is useful, but it's troublesome because as you have seen here, it's cumbersome to write out all the bonds, and sometimes key details are being hidden. Um, which of course for ethane diol acid is fine because there's only 2 carbon. Let's say I give you a 10 carbon compound, and then you go and draw all the CH bonds, and then the key functional group which you want for discussion is not displayed for you to I mean to showcase its importance. So sometimes these details are actually important, and the rest of the long chain are not important. So usually we use a simpler representation, what we call a skeletal formula. Okay, so this is where I want to introduce you to this way of writing known as a skeletal formula. So basically for a skeletal formula, you don't show the carbon and the H. So in this case, I'm just going to run you through the same idea. So if you look at this, it's like this. So actually there is a carbon here, but I'm not going to showcase it. Okay, and then there's a double bond here. Okay, so I'm just going to put an O. Yeah, so for heteroatom meaning atoms other than C and H, I need to show them. Okay, if not, I wouldn't know whether this is O, this is C or N. Okay, then of course OH, I just put it like this. Right. So what I've drawn here is what we call a skeletal structure or skeletal formula. Okay, so this skeletal formula. Skeletal formula is cleaner and it gives you a detail. So from here straight away you know that I have 2 carboxylic acid functional group in ethane diol acid. Yeah, so that's the main thing which I want to emphasize. And usually when people draw it like that, they want to emphasize maybe on the acidic behavior of ethane diol acid. Okay. Are there a lot of in-betweens? Yes, there are a lot of in-betweens. So sometimes if you feel like it, you can showcase one of the bonds out from here. Maybe because you want to show how the H is being removed from the OH. Yeah, so there is nothing wrong in showing a skeletal formula where some of the bonds are shown. Like let's say if they're sigma bond, you show them as sigma bond. It's perfectly fine. Don't worry about it. Okay, so this is the skeletal formula which is we don't really give it a name. It's not partial or what. It's just a skeletal formula with some details, some additional details. Okay, yeah. There's also another formula which I want to bring to your attention. It's known as condensed structural formula. Yeah, so the word condensed structural formula. So for condensed structural formula, right, the bonds may or may not be shown. It looks like a molecular formula, but it is not a molecular formula. So it's CO2H, CO2H. Okay, so for the case of ethane diol acid, it can be shown like that. CO2H, CO2H. Or maybe another representation would be HO2C, CO2H. Yeah. So in these two condensed structural formula, there is no ambiguity. Then you might argue, why is it that there's no ambiguity here? Okay, there is no ambiguity because if you try to draw the structure out, right, there's only one way you can draw, which is like this. Okay, if you don't believe, you can try. Yeah. So for condensed structural formula, although the bonds are not shown, right, based on the way the letters are arranged, you can sort of tell how are they drawn. So for example, CO2H here, obviously there's a carboxylic acid group. So if you draw a carboxylic acid group here, okay, you wouldn't be using any of the other atoms other than carbon, right, to bond to the other carboxylic acid group. So I hope you know where I'm coming from. Yeah. Same goes for this, because this is just the first portion here is just the carboxylic acid written in the reverse order, which is fine. Okay, although sometimes it's not encouraged. Yeah, so these are the 5 formula which I thought I could introduce to you, so that you get a clearer picture on how do you showcase, or how do you display your appreciation of organic chemistry structures. Okay. In the past, student actually asked me questions like, why are skeletal formula zigzag like this? Why is it zigzag? Let's say for a butane, decane, we write it as zigzag. The reason why is it zigzag is also historical origin, because okay, maybe this is too long, so maybe I'll just do for hexane. Okay, so if you look at it this way, right? Can you try to visualize that if each carbon were to be tetrahedral, okay, then I'm going to end up with something like this: HH, and then H, 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 and then H, H. Could you all imagine? Okay, I'm not sure. So there's a H here, 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 H, and then another H. Oh, sorry, and then another two H's below. Okay, and if you recall, earlier on in my introductory, not introductory, in my bridging video, I was sharing with you the projection. Okay, so I'm going to showcase for methane. So for methane, if the H is projecting out of the computer screen, it's shown by this bow representation. Okay, and if it's projecting away, it's shown by this hash. Okay, so H, 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 okay, H, H, like this. Okay, I'm not sure whether you remember it. Yeah, so same case goes for skeletal structure. So for skeletal structure, right, you can visualize each of this CH2 as one projecting towards you, towards you, towards you, towards you, and the other one projecting away from you, away, 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 away. Yeah, so that is why it's written in the zigzag format. Yeah, of course you may ask, can I write it like that, like that, like that, like that, like that, like that, or any other way? You can. It's not a problem. It's just that you are kind of like wasting space. Okay, that's number one. And then of course number two is like sometimes if you orientate in a weird manner, your mind cannot read it fast enough, and then you will end up making mistakes. So maybe my suggestion is don't write it in weird ways until you are very familiar with what you're doing. Okay, yeah. Then of course I don't have to show you how to draw the rings. Okay, so yeah. So I'm going to go back to the lecture slides. Okay, yeah. So I think essentially I've covered everything I need to cover. So except that for this particular page, they use lactic acid as the example. Okay, so they have covered empirical formula, which I've done, molecular formula, structural formula. Okay, so in this case, this structural formula, right, is what we call the condensed structural formula. Okay, some students will ask, is it okay to write like this? Like let's say I give a partial display. Okay, if it's called a partial display, if you want to call it partial display, it shouldn't be called a display formula. You just call it another kind of structure formula. Okay, so like that. Yeah, some students ask, can I draw like that? Yes, you can draw like that for structure formula. So basically, structure formula is in any ways you want, like that you are comfortable with. Okay. In particular, condensed structure formula, right, usually do not show any bonds in it. So I cannot call this a condensed structure formula. This is just a structure formula in your own way. Okay, so I hope you know where I'm coming from. Displayed formula, all the bonds must be shown. I think I showcased earlier on. Ring, learn how to draw at least a hexagon well. Okay, learn how to draw a hexagon well. Don't need to use ruler. You are not allowed to use those kind of model templates in exams, so learn how to draw it using freehand. Okay, benzene ring, just put a ring in the middle. So this ring in the middle actually represents delocalized electrons amongst the 3cc double bond. Okay, so the 3cc double bond in benzene delocalized around the ring, and that's why it gives rise to this particular ring current. So we usually just put a circle around it. Okay, And then skeletal formula gives you the details you need. For example, one look at this, I know that lactic acid consists of a secondary alcohol and a carboxylic acid. So the secondary alcohol is here, the carboxylic acid is here. Okay. You can draw partial skeletal representation. So basically, any way you want, it doesn't matter as long as they are unambiguous. The keyword is unambiguous. As long as you understand this term, I think you'll be okay. Okay. And normally we will write the longest chain in the zigzag format. So for example, in the case of lactic acid, right? Like we'll write it this way because the longest chain is 3 carbon. Yeah, so usually then you ask, if I write it like this, will I be marked wrong? Okay, you won't be marked wrong, but it's just not conventional, but it's fine. Really, it's fine. So don't worry about it. Yeah. Stereochemical projection, I give you a brief introduction. So like the solid wedge represent bonds projecting towards you, or sometimes it's coming out, pointing out of the paper. I prefer to call it projecting out of the computer screen since you're watching this online. And then the dash or the hash represent it projecting away from you or projecting into the screen. And then usually the solid lines represent on paper. Not always the case because sometimes it's a bit tilted, but you can take it as it is at face value. Okay, now so for exercise 3.1, you are supposed to complete the table by writing the different types of formulae for compound A and B. Okay, so for this particular compound, we'll just do B first because the skeletal structure appears over here. So normally you can just count in your heart, like how many carbons are there. So if I do a quick look, there are 6 here, so that will be a C8. Okay, so it's a C8. How many H? 5, 6. Okay, usually this is being missed out, so take note of it. Yeah, how do you remember like how many H are there? You just count the number of bonds because each carbon can only form 4 bonds, and this particular carbon already formed 3, so the fourth one must be a H. Okay, so we have 5, 6, and then 7, 8, 9, 10, 11, 12, 13, 14, 15. So H 15, Cl. Okay, maybe I want to put it across categorically that this is actually very bad practice in drawing out the H because if when you are at the advanced stage, you shouldn't be drawing out the H's. Okay, it should be kind of like, you should be able to count it fast, like 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, something like that. Yeah, but I think at this stage it's fine. You can just doodle a bit. Okay, so empirical formula is the same because there's only 1 Cl. Okay, displayed formula, you don't have to draw out the displayed formula for your ring. Because in your learning objective it's written that for ring you can just keep it as ring. Okay, but for the rest you can draw them out nicely. So CH2, C, H, H, and H. Yeah, something like that. Okay, and then of course the skeletal formula will need no introduction, just like this. Okay, sorry, I need to connect them properly. Yeah, like this. Okay, so now I have a skeletal formula showing me this group, the CN group. Okay, so usually, maybe my advice is, for C triple bond N, right, we call this the cyano group. Usually we try not to showcase the skeletal like this. The reason is, if I don't remember wrongly, quite a lot of students usually get confused with it. So we can just write it as CN. It's fine. Like, you will not be penalized for such skeletal structure. Okay, yeah. But of course, if you want to write it as C triple bond N and you can see it, then no problem, go ahead. Okay. For the displayed formula, it is really troublesome. So you have to draw out every single bonds. But yeah. So I'm not sure whether I can tell you to rest assured that we will not test you in exams, but You know, sometimes if you need to draw the displayed formula, we will test you. No choice, especially maybe for promos. Okay, because nothing much to test anyway. Yep. Okay, so CH3, H, 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 and then C and H, H, H. Okay, let me also explain one of the most common error that student will make for when they draw displayed formula. They will write this as OH, and then maybe this as CN. Okay, so straight away for a displayed formula, if there is one bond not being shown, then it will be marked incorrect. Okay, unfortunately. Yep. And then for the structural formula, we can just write it as it is. So I'm going to write the condensed structural formula. So I will write it as CH3, okay, and then CHOH, and then CHCN, okay, and then after that CH2, CH2, and then C, and then CH3, 3. Okay, so I hope you know where this is being linked to. So if you need some help, okay, so the CH3 is here. Okay, then after that the CHOH is over here, and then the CHCN is over here, and then of course the CH2, 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 and then the carbon, and then CH3, three of them, like this. Okay, so it's unambiguous. Yep. Okay, so for the molecular formula, I just need to do a quick count. I should get C10, H19ON. Okay, so same thing, C10, H19ON. Same for the empirical formula. So not very inspiring. Yep. Okay, I'm going to move to the next part quickly. Again, this portion, nomenclature, has always been an issue because for beginning students, you will be thinking that, oh, I have to go and memorize how to name, etc. But I think at this stage, again, as I emphasized earlier on regarding the functional group, please do not be too absorbed by the functional group names. You learn them as you progress through your organic chemistry. Okay, so for organic molecules, okay, so basically there are two different types of names which we are familiar with. One is what I call the common name, like common name, for example, for vinegar. Okay, what is present in vinegar is called acetic acid, but you don't usually call it acetic acid if you use the IUPAC nomenclature because there are two carbons, so we call it ethanoic acid. Yeah, so menthol, that's another one. It's a complicated looking alcohol, but we don't call it menthol in the IUPAC naming, so it's a super huge, super long names. So there's always been a debate like whether we should just call the organic compounds the systematic name, otherwise known as the nomenclature, or we should just call it its common name. So I have to say that in such cases, most of the time we just call it the common name because it's a common language between most chemists. The systematic name is just to give it an unambiguous naming for academic purposes. That's about it. Yeah, but do not be worried about the difficult naming because you won't be tested on them. Yeah. Whatever you'll be tested are usually the simple kind of naming. Okay. So if I want to go a little bit into details, it will be something like that. So for example, we have this this particular unknown. It's a carboxylic acid, right? Yeah. So we will number it from right to what? Okay, you might be wondering why do we number it from right to left? Why not from left to right? Okay, usually carbon number 1, right, is taken to be the functional group that is given a higher weightage. How do you know? Okay, you don't know. It should be told to you. Either from the IUPAC nomenclature or what, but I have to say, usually carboxylic acid has a greater so-called priority or heavier weighing as compared to, let's say, OH. So because it's given priority, so the number is 1. So when you look at this unknown, right, you just count the number of carbon. So there's 1, 2, 3, 4. So the longest chain has 4 carbon. Okay. If you are tempted to look at the rest, actually only 3 carbon. Yeah. So the longest chain is 4 carbon. So for 4 carbon, right? Of course, it's the main acid is butanoic acid. So we call this butanoic acid. Yeah, 4 carbon, so it's butanoic acid. Yeah, but because it has substituents, so we need to learn how to name the substituent. Okay, so we name it by looking at their relative position. So in this case, the methyl group, there are 2 methyl groups at the second position. So we call it 2,2-dimethyl butanoic acid. Okay, but there is another substituent known as the hydroxyl, which is right at the end. Okay, you don't call this the alcohol if it's part of the substituent. The reason is the main character here, okay, the main person, I mean the protagonist, you know, call it, is actually butanoic acid. Yeah, so once the OH is no longer a proper functional group here, where it's just part of the substituent, we don't call it the alcohol. So we will call the substituent hydroxyl. Okay, locant is just to indicate the position of the unknown, or rather of the substituent. Okay, yeah. So if you draw this out in skeletal structure, okay, let me just show you in ChemDraw. Okay, so if you draw this out in skeletal structure, it will look like this. Okay, so it's butanoic acids. Yeah. And then 2 substituents here. Okay, so 1, 2, 3, 4. Then there's a hydroxyl. Okay, so its skeletal structure will simply look like this. Yeah, so this is 4-hydroxyl 2,2-dimethyl butanoic acid. Yeah, so let me just show you in reality. We don't really need to name it because the computer can name for us. So I just go to this and I just put convert structure to name. Yeah, so this is the name. Yeah. Okay, so yeah, so in reality, scientists don't really need to know how to name. Like I don't need to know how to name because I can just rely on the program. So you just name for me. Okay, then you'll be wondering, if I name wrongly, what's going to happen? Okay, so for example, I just give you a random example. Let's say you somehow you name this wrongly, okay, for some reason. Let's say you call this 4-hydroxyl benzoic acid. Yeah, I mean you just call this 2,2-dimethyl 4-hydroxyl butanoic acid. What's going to happen? Actually, it doesn't matter because you can still get the structure. It's still the same structure. Do you realize it? Yeah. So actually, the naming is more of an academic interest rather than who is right and who is wrong. Even if you name it wrongly, I think chemists will still know what you're trying to say. Okay, yeah. So imagine a complicated, I mean, a relatively simple structure that looks like this, right, can have quite a complicated name. So sometimes chemists will be thinking, or I will be thinking, is there really a need for IUPAC naming? Yeah, so for this particular structure, you look at the name. Okay, this is considered relatively short, but if I just make some side chain, then it will be very long. So nobody in the right mind is going to name it. Okay, but anyway, I don't think this is very important here. Okay, so I'm just going to go back to this. Yeah. Okay, so the naming, I'll just leave it up to you. There really isn't a need to be too worried about it. Okay, but it will be good for you to know LQ, like the LQ chain or all these side notes like math. I think I talk about this in the introductory or rather the bridging course. So it will be good for you to know until 10. Okay, if not at least until 6. Okay. I think all this you just learn them as and when it comes to you. I don't think you need to be bothered by it. This is why this was what I mentioned earlier on regarding the priority. Yeah. So carboxylic acid actually has the highest priority. So that's why just now that molecule is known as blah blah butanoic acid rather than butanol. Yeah. Okay. Alcohol has a lower priority than carboxylic acid. So that's why it's named it's not named an alcohol, but it's named as a carboxylic acid for the earlier compound. Yeah. Okay, then these are like what I mentioned earlier on. Like for example, if it's a mixture of carboxylic acid and alcohols, then carboxylic acid is actually the parent, meaning the one given a higher priority. Then the OH you no longer call it an alcohol, you call it a hydroxyl group. Yeah. Okay, so that's how the naming comes about. Okay, again, as I said, if you need this, then you will look at it as and when it comes. Yeah, the locum represent showcase the positions. Okay. Yeah, so I think I mentioned just now how do you count your carbon is also very important. Okay, of course there are some common names, like for example phenolamine is actually a common name. Yeah, the proper name for this is actually called aminobenzene, but I mean if you call this aminobenzene, people look at you with a strange look. Yeah, so we just call it the common name phenolamine. I think everybody understood what phenolamine is. Okay, so let me stress again. Do not be too stressed over naming, as well as trying to remember all the functional group, because when time comes, then it's worth studying them, and then slowly but surely it will get into your memory. Okay, if you start to worry now, I think you'll just kill the joy of learning organic chem. Okay, for exercise 4.1, we are just going to go into drawing. Yeah, so I'm actually quite tempted to just copy this into ChemDraw and then just copy over, and then the structure will just come out. But yeah, we'll do the draw, we'll do the naming and the drawing together. Okay, so the first thing is 2,3-dichloro 3-methyl-pentane. So the first thing we need to do is we identify the parents, which is pentane. Okay, so the parent is pentane, so I'm just going to draw out 5 carbon. Okay, so that's 5 carbon, and then we have a 3-methyl. Okay, so at the third position, there's a methyl group, and then we also have 2,3-dichloro. Okay, so it doesn't matter whether we number it from left to right or right to left in this case. Yeah, because again, it doesn't matter. Okay, so anyway, 3-methyl is here. Oops, sorry, 3-methyl will be here. Okay, third position. Okay, so maybe just let me number 1, 2, 3, 4, 5, and then at the second position there's a Cl. Okay, and then at the third position there's a Cl. Yep. Okay, so this will be the structure for 2,3-dichloro 3-methyl-pentane. Yep. Okay, and then next we have 3-methyl-but-2-ene-1. Oh wow, that's quite a mouthful. But not to worry, we'll look at it slowly. Okay, so we look at the parents first. Is but. Okay, basically it's an alcohol with an alkene. Okay, and the alcohol is at the first position. Alkene is at the second position. Okay, so just going to try to draw it out first. Okay, so we're going to draw the alcohol here. We are at the first position, so we call this 1, 2, 3, 4. Okay, so once we number it as 1, 2, 3, 4, we look at the position of the alcohol. Is correct. The double bond starts with carbon 2, so definitely not 2 to 1. Okay, it's 2 to 3. So remember, the lowest number comes first. Okay, so when it's 2 in, then it's from 2 to 3. It's not from 2 to 1, because if they want you to name something from 2 to 1, they will call it build 1 in, 1 or, but they will not name it that way. Yeah, okay, so like this, and then after that, there's a 3-methyl, so that will be a 3-methyl group. Yeah, so that will be our answer. Okay, then what are the systematic name to the following compound? So, well, I mean, this gets a little bit complicated. So again, I'm very tempted to just use ChemDraw to go and name it, but okay, so we have to go through it. Okay, so first we need to understand what functional group is present. There's an alkene here, but there's a cyclohexene, right? So because there's a cyclohexene, let's try to number the carbon. So there's 1, 2, 3, 4, 5, 6. Yeah, so we tend to be I mean, we may be tempted to number it this way, but this may not be correct because remember, alkene always takes the lowest priority. So if we have alkene, then the alkene should be numbered as number 1. Okay, so in that case, I should erase all of these. Okay, so I should start to number from here. So that's 1, 2, 3, 4, 5, 6. Yeah, so this is a cyclohexene with the third position having 2 methyl group. So we call this 3,3-dimethyl. Okay, cyclohexene. Yep. So if you are in doubt, we can always use ChemDraw to double confirm the naming. Okay. Okay, so yeah, that's why I said with technology we don't really need to name it. Yeah, so this, and of course they are okay. I think we have to be more accurate, which I agree. So we have to call it hex 1 in. Okay, to be really explicit about it. Okay, so yeah, maybe we change it hex 1 in. Okay, the reason why we need to be so explicit is because if I'm going to shift the double bond to let's say the other position, right, then it's going to add to the complication. Okay, so let's say I have this, although it's still hex 1 in, yeah, but I think it's making the name a little bit more unambiguous. Yeah, so I think the hex 1 in is quite crucial when it comes to the naming. Okay, at least for this compound. Okay, so we're going to this. How are we going to name this particular compound? So again, we do the same thing. Earlier on, if you remember, carboxylic acid takes the precedence. So that's carbon number 1, 2, 3, and then 4. Yeah, so again, this is some form of butanoic acid. Butanoic acid. Okay, so what are the functional group present? So we have a NH2, which is an amino group, and then we have an extra methyl group here. Yeah, so if we complete the picture, second position there's amino group, so it's 2 amino. Okay, 2 amino, 3 methyl, butanoic acid. Yeah, so that completes the naming. Okay, yeah. Exercise 4.2, draw the structures of the following compounds. So tetrafluoromethane, again, you have 4 fluorine around the carbon. Okay, the methane doesn't mean I have a CH4. The methane here simply means there's 1 carbon, which is an alkyl, and then each of the H is being replaced by F. Okay, 3-methyl cyclohexanol. So if we draw a cyclohexanol, okay, OH here. So this takes position 1, 2, 3, so 3-methyl. That's here. Okay, and then 3-ethyl benzene. So we have a phenyl ring over here, and then we have an ethyl substituent. Okay, and then 1,2-dichloroethane. So again, an ethane structure. So that's 2 and 1, and then with a Cl on the left and right. Yeah, so this 1,2-dichloroethane. Okay, systematic names for the following. So again, following the same idea, this is a nitro group, so we just call this nitrobenzene. Okay, and then same thing, aldehyde. 2, 3, 4. Yeah, so you'll be surprised lah. I mean, how do you know that this is an aldehyde? Okay, so aldehyde is written as CHO. So an aldehyde usually have R group here, and then with a carbonyl group that looks like this. Okay, this is carbonyl group, and then the one side is a H, the other side is a R. So we call this an aldehyde. So because it's an aldehyde with 4 carbon, so we will call this butanol. Okay, and the third position has an OH, so we call it 3-hydroxybutanol. Okay, 3-hydroxybutanol. And okay, so one more here. So I think we need to sketch out the structures in order to name it in a proper way. So we have a carboxylic acid over here with 3 of this group. Okay, so let's see if I'm right. Yep. Okay, so again, if we do a quick count, 1, 2, oops, I think I've drawn an extra one. Okay, so let me erase it again. Okay, so 1, 2, okay, it's like this, like this, like this. Okay, so just 2, 3. Okay, so 3 carbon, so that's propanoic acid. So how many extra substituent? We have 2, CH3, CH3. So we will call this 2,2-dimethyl propanoic acid. Okay, so I think we should write them closer. 2,2-dimethyl propanoic acid. Yep. Okay. So again, I think drawing skeleton helps. So it looks like this. Like this. Okay, 1, 2, 3, 4. Yep. So this is 4. So it's butene, but because there are 2 CC double bonds, so we call this but. 1, 2, 3, 4. So first and third position. So it's butyl 1, 3 diene. Yeah, because there are 2 alkene, so we call this diene. So that's how you name it. I think you can view this from this particular portion. Yeah, on how do you actually add the required prefix. Like if you have 2 CC double bond, we call it diene. 3 we call it triene. Yeah, something like that. Okay, but again, if you need it, then just come over. If not, then I think you can just leave it as it is. I don't think you need to worry too much about all this. Okay, section 5 is probably the most important section in this particular introductory organic chemistry lecture, because we are going to focus on some of the key ideas in reactions involving organic reagents. Yep. Okay, so there are a few types of reactions or types of reactions which you need to be aware of. So we're just going to go through them, but again, let me emphasize, you do not need to memorize them at this stage. You know, like once you study them, get used to how they are formed, their terminology, and some of the patterns which are common. So once you're able to do that, then I think you'll naturally be able to internalize some of these ideas, and this will actually help you to appreciate all this better rather than just purely trying to remember all the facts. Okay, so the first category is what we call substitution. You might have heard of it from secondary school. So so basically one thing substitute for another lah. So in this case, I think in the example given to you, X is being substituted for Y. Okay, yeah, and then so example is you have a Cl here. Okay, is being substituted by OH minus. Yeah, so this is known as substitution reaction. Okay, yep. Another type of reaction which you might have come across is known as addition. So addition is usually we say it adds across the double bond or it adds across the triple bond. Yeah, so usually for addition reaction, right, there is no nothing is being lost in the process of the reaction, which means there's no byproduct in the course of reaction. So for example, when the C double bond is added, when YZ is being added across the C double bond, then nothing is being eliminated in that sense. Yeah, so we call this a pure addition reaction. Okay, so basically one pi bond is broken, and then you form two new sigma bonds at the organic substrate, of course. Elimination is the reverse of addition. Yeah, so you can see from the same example, right, I eliminated YZ away. Yeah, so similar examples is shown here. I just want to bring to your attention that these are just representation of the reaction, but of course in reality it could be more complicated than what we showcase here. Okay, and then condensation is something that you have learned before in secondary school, although it's the common last topic, but I have briefly mentioned that in the bridging module. So for condensation reaction, basically it involves two molecules. After reacting, they actually release a small molecule such as H2O or HCl or some other molecule. Yeah, so this is known as condensation reaction. Okay, so hydrolysis is usually the reverse of condensation if it involves water. Yeah, so the reverse of this is known as hydrolysis, which is showcased here. Okay, of course this is just colloquial terms, like the molecule is being split or is being hydrolyzed is a better word. Yeah. Okay. You might also maybe at this point in time it's good to sort of mention that condensation reaction in most cases can be broken down into two bits. The first bit involves an addition, and then this is followed by elimination. Yeah. So for condensation reaction, in some sources or in a slightly more advanced textbooks, they will call it addition-elimination reaction. Yeah, so addition-elimination is another term for condensation. Okay, but of course for H2, you should stick to the usage of condensation rather than addition-elimination. But it's good to understand what it means. Oxidation here usually refers to what happened to the organic substrate rather than what happened to the inorganic substrate. Yeah, because if your organic substrate is being oxidized, then your inorganic substrate is being reduced. So when we say that oxidation occurs in organic reaction, it doesn't seem to make sense because by right it should be redox. But yeah, so usually these two words are taken from the perspective of the organic substrate. It's understood, but sometimes we need to explicitly mention it. Yeah, so usually for oxidation reaction, you can actually count whether there's an increase in oxidation state as a whole, or the particular carbon which is involved, or you can roughly do it by inspection. So if you realize that there is an increase in oxygen or there's a reduce in hydrogen, yeah, so usually it involves oxidation. Yeah, so for reduction it's the other way around. There's a decrease in oxygen or increase in hydrogen. Okay, so this particular portion is a little interesting. That's the writing a balanced redox equation in organic chemistry. So normally for organic chemistry, we do not. Okay, maybe I shouldn't say we do not, but to save time, we usually represent the so-called the addition of O with a bracket O, without bothering to balance them in the stoichiometric ratio with the correct oxidizing agent. So for example, if you are oxidizing methanol to methanoic acid, we just represent it like that with a bracket O. So there's a 1 here, but of course 1 we don't write it. And then for the reduction of methanol to methanol, we just write 2H. Yeah, so this is the usual way we write it, but sometimes in certain circumstances we will need you to showcase the number of electron transferred or things like the number of moles of oxidizing agent used. Let's say, can you write me a balance equation between methanol and let's say an oxidizing agent such as potassium dichromate, something along those lines, then I will need to see whether you know how to write the correct balancing. Okay, so but in most cases, I think with a bracket O and bracket H, it's good enough. Yep. Okay, so for exercise 5.1, we are just simply looking at what are the type of reaction that has been taken place. So again, you notice that for our case here, the Br is being replaced with the NH3, sorry. Yeah, so of course we will call this a substitution reaction. Substitution reaction. Okay, so it's some form of substitution. Some of you might be wondering, how come one of the H is gone? Well, because when ammonia actually replaces the Br, the intermediate product is actually a CH3 and H3 plus. Yeah, yeah. So it's actually the N will have a former positive one charged. So of course, one of the H is being lost as a H plus in order to generate the amine which we want to generate. So that's usually the case. Okay, then you notice that the OH is now, or rather there's a loss in H, and there's a formation of a new CO double bond. Yeah, so you would expect this to be some form of oxidation, okay, of the organic substrate, of course. Okay, there's a small molecule given off, which is HCl. So you expect this to be condensation. Okay, or you can call it addition elimination if you wish to. But before you fully understand what addition elimination is, I think it's just better to call it condensation. Okay, and of course in this case, HCl is added across the CO double bond, so we call this an addition. Yep. Okay, so in this case, you were told that potassium dichromate can be used to oxidize ethene to carbon dioxide. Write a balanced equation for this oxidation of ethene. Okay, so we're just going to, okay, I will use this example to showcase to you how to write the actual redox balancing, but I'm just going to use the organic nomenclature, or rather the organic way of writing, in terms of the bracket O's first. Okay, so in this case, it's not difficult because all we need to do is, we know that CO2 is being given off, right? Okay, but we have two carbons, so 2 CO2 is being given off, and then H2O, because H is, well, I mean H remains as +1, so definitely we have H2O, so we have 2 H2O. And then all we need to do is just to do a quick count in the number of oxygen. So we have 2 oxygen in water, and then 4 oxygen in CO2. So when we write the organic balancing, it's basically just 6 bracket O to get CO2 and H2O. Yeah, but if so whatever I've written here, right, is enough to satisfy this question. Yeah, but for those of you who are interested in the actual redox balancing, okay, the actual redox balancing, then you need to go back to the way we write it for electron transfer. So how do we do that? Okay, so for C2H4, right, if you do a quick calculation, the average oxidation state, or in this case, no need average, the actual oxidation states for carbon here is actually -2. I don't know if you realize it's -2. Yeah, because in this case it's 2x plus 4 equals to 0. So x is equals to -2. And then in the course of the reaction, I'm generating 2 CO2 here. So each carbon, the oxidation state is +4. So in total, 12 electrons is being given out. You noticed 12 electrons. Why 12 electrons? Because each carbon gives out 6, so 2 carbon will give out 12 in total. So if 12 electrons is being given out, then we need to do the correct balancing, right? So because permanganate usually we use the acidic medium kind, so in this case we should write a 12H plus here to balance off the electrons. And then you do a quick calculation, you realize that I will need 4 H2O. Okay, 4 H2O because there's a total of 12 H on the right hand side, but on the left hand side I only have 4 H's, so I need 8 more H, so that's 4 H2O, and it will also help to balance the CO2. Okay, so maybe I will write it here, 4 H2O. Okay, so I'll just erase this. And then for the case of permanganate, you can just check your data booklet. So MnO4 minus plus 5 electrons plus 8 H plus. Then I'm going to get Mn2 plus 4 H2O. Okay, so what you're going to do now is you're supposed to add the two equations up, and you realize that it's actually more complicated than it seems, because if you simply look at electron transfer, one of them is ethene give out 12 electrons, but permanganate can only take 5. Yeah, so if you do a cross multiplication, so you multiply this by 5, so I'm going to get 20 H2O plus 5 C2H4, okay, plus 12 MnO4 minus plus, so the electron will cancel, so multiply by 12 times 8 is 96 H plus. You realize that the numbers grow very big, and then 10 CO2 plus 12OH plus, that's 5, sorry, not 12OH plus, I multiply the top by 5, right? Yeah, okay, so not 120, that's 60H plus, and then plus 12 Mn2 plus 48 H2O. Okay, so I'll simply just do cancellation over here, so that's all gone, and I'm going to have 36 H plus here, 48 H2O, so this is gone, and I'm going to end up with 28 H2O. Okay, and that's it. So you see that the actual balancing, it requires a lot more time than the short form you require for organic chem. Okay, yeah, I hope this kind of like give you a clear picture. So for assessment purposes, if we need you to do the actual balancing, it will be quite clear from the question. Okay, next, for the mechanisms of organic reaction, you'll notice that one of the important learning objectives here is that the students are expected to interpret and use the curly arrow notation to represent the movement of electrons in organic reaction mechanism. So only organic. Okay, so the mechanism, it gives you a snapshot and maybe a pictorial representation of bond broken and big bonds being formed. So I will not go too much into details, but just for you to take note that the curly arrow notation represent the movement of a pair of electrons if it's a full arrow like this with full arrowhead, and then if just a half arrowhead, we call this the movement of a single electron. Okay, usually by convention, you start off with an electron rich region and you end up with an electron deficient region. So for this curly arrow, we start with electron rich and then end up with electron deficient site. Yeah. For single electron movement, it doesn't really matter, because for radicals, or let's say it's a homolytic cleavage kind of reaction, then it doesn't matter where it's rich and where it's poor. Okay, but most of the time you'll be using a full arrowhead. Your full head arrow. So in that sense, it's important for you to recognize where is the electron rich and electron deficient region. Okay, so you have heard me talking about this term known as homolytic fission or homolytic cleavage. You saw this in your block test as well. So basically, when we say that the XY bond is broken, when we subject XY to its bond energy, yeah, so it will be broken homolytically, where each of the X and Y will take back their electrons and each of them will end up as a radical. Yeah, so free radicals, you need to know this definition. It's a species containing unpaired electrons. And of course, they are highly reactive because they are desperate to either gain back the electrons or to react with something else in order to attain the noble gas configuration. Okay, so if you have a homolytic cleavage of a CH bond in methane, we'll end up with a methyl radical and a H. Take note that the number of electrons around the carbon in the methyl radical is actually 7. Okay, which makes sense because if you do a quick drawing of the dot and cross diagram, you'll realize that there are 7 electrons around carbon. Okay, I think it's shown over here. Okay, and then heterolytic fission here means that one of the atom will take both the electrons. So in this case, it is usually the more electronegative elements. Yeah, so you will form a cation and an anion. Okay, so yeah, so normally this is how carbo-cations are being formed. So if you do a quick count here, what exactly is a carbo-cation? Carbo, as the name implies, is a carbon-based cation. So when this homo or heterolytic cleavage occurs, you get a chloride anion here and a CH3 plus with 6 electrons around the carbon center. So we call this electron deficient. Yeah. So therefore, any species with lone pairs of electrons willing to donate to the carbon center will be welcome, and a reaction will immediately take place. Yeah. Okay. What about heterolytic fission? So if carbon is bonded to an element that is less electronegative than itself, or carbon is more electronegative than that particular element, then heterolytic fission occur, and then you will form what we call a carbon anion. So again, a carbon anion is different from a carbocation in that the carbon anion has 8 electrons around the carbon, not 6 or 7. Okay, yeah. Okay, so in this case, it can be a little bit complicated for beginning students sometimes lah. Like what exactly does it mean by electron movement? Okay, so I think usually the part that is maybe it's a little bit challenging is the movement of single electrons lah. Yeah, so it can be a little bit challenging for beginning students on this lah. Okay, so single electrons here, it's like, let's say I have a Z radical lah. Then I want to form a ZX single bond. Okay, and of course you know that Y is being kicked out, so-called, as a radical. So I think the first thought process that you will have is you can actually work it out in this format lah. You can visualize it as maybe some form of heterolytic, or rather homolytic cleavage. So in that sense, you end up with 2 radicals. Okay, and then the X radical, okay, will then combine with the Z radical, okay, to form the ZX. Okay, but however, in this case, right, it actually happens so-called simultaneously, which means I mean just for this case lah. So it doesn't break first and then form. So because it's happening simultaneously, right, then instead of writing it out in 2 steps, yeah, so we will then try to link them up. So instead of this going to the X, so I'm just going to erase this. So we'll straight away say that, okay, this electron will then combine with the one I have from Z. Yeah, then in that case, we don't have to draw this step. Yeah, then we also don't have to draw this particular step. Yeah, so you can just combine these together. Yeah, so that's what is happening lah at least at this level. You might notice some textbook actually allowing the students to write just directly going like this. It's actually okay as well. Yeah, so this arrow is kind of like additional. I won't say redundant, but just additional. Yeah, but I think it makes it clear that your Z is also introducing that single electrons to form that sigma bond. Yeah, so usually for H2, we will want to write in that so-called additional arrow. Yeah, just to complete the picture. Okay, but in most cases for H2, you will most of the time encounter movement of electron pairs. For in this case, the lone pairs of Z attack the X, so you can view X as an electron deficient site, and then maybe Y as an electron rich site, and then so the bond will break towards the Y. Yeah, so normally in the terminology of organic chemistry, I'm going to introduce you to a new terminology. Yeah, we can call this Z lone pair and electron source. Okay, and then the Y and electron sink. Yeah, so electron density usually goes from source to zinc. Yeah, so you push electrons. Yeah, so in organic chem we call this arrow pushing, which means to showcase how electron pairs move in the course of a reaction. So when we do this, we say that electron pairs always goes from source to the sink. You don't see two sources coming together for a lone pairs. So this is entirely wrong. Yeah, so you can see that when electron move, I mean, when you showcase electron pair movement, it goes from the source to the sink, and then the source to the sink. Yeah, yeah, source to sink, source to sink. Yeah, so that's how you can understand it. Okay, yeah, and then polar reaction and their mechanism. Okay, so generally, if reactions involve electron pair movement, which means showcasing movement of lone pairs of electrons, right? They are usually polar in nature, so meaning that there must be a rich and a deficient site. So the electron rich site, right? Just now I call this the electron source, and then the electron deficient, we call this the electron sink. There is another term in organic chemistry which you all need to know. It's called the nucleophilic site. So in this case, we will call an electron-rich site nucleophilic, and then an electron-deficient site electrophilic. Yeah. So these are two additional terms you want to know in organic chem. Nucleophilic site, sometimes we call them Lewis basic. Electrophilic site, we call it Lewis acidic. Yeah, these are just terms as well. Yeah, okay, so again, same thing, electron lone pair attack the carbon, which is the electron sink, okay, because it's electron deficient, and then the sigma bond break towards the Br, okay, and you get this. Okay, yeah, so in this case, we say that the OH minus acts as the nucleophile because the carbon is electron deficient, so it is susceptible to nucleophilic attack. Okay, yeah. So there's a definition of electrophile and nucleophile here, so I'll leave it to you to look through them. But basically, an electrophile will tend to accept electron pair to form a new covalent bond. Nucleophile will tend to donate the electron pair in order to form a covalent bond. Yeah, so nucleophile and electrophile are just terminology that is frequently used in organic reactions. Yeah, okay. There's a historical origin of the two terms nucleophile, electrophile. If you wish to know them, you can actually Google it and then maybe watch some or read some history about them. Okay. Other than that, they are just terms with some historical baggages. Yeah, because nucleophile actually means nucleus loving, means they love positively charged centers. Yeah. Maybe over here I want to point out to you, but again, it's only when you make mistakes that you learn. The placement of each curly arrow is very important in organic chem. So the tail must start with either an electron pair or a pi bond. Okay, not the charged. Okay, and then you must point towards where the new bond is being formed. So that means that if let's say I have a random carbocation here, like for example, and I have a let's say a cyanide. Let's say I have a nucleophile. It is actually incorrect to point like this. Yeah, so this is incorrect. The proper way is you have to point at where you're forming the bond. You're forming the bond with the carbon, not the charged. Yeah, so we are quite precise here. Unlike maybe some of you might experience in chemistry Olympiad where they start to push the electrons from the negative charge and then they just anyhow end up anywhere. I think in H2 we are following the British curriculum where you have to be very clear where the lone pairs is being transferred to. Okay, so remember it has to be exact. So I hope none of you will make the mistake of starting electron pair movement from the charge. Okay, yeah. So for non-polar reactions, usually it's radical based. So like what I said, what I mentioned just now, like for example, the combination of these two single electrons will give rise to a new covalent bond. So this single electron is now pushed towards the other single electron. So normally we will showcase both the half arrowhead rather than just a single arrowhead like this, a single half arrowhead like this. Yeah. So the convention for H2 is usually we showcase two fish hook arrows or two half arrowheads. Yep. Okay. Um, I'm sure some of you might have a lot of questions now, so please clear them up during our tutorial sessions, so that anything you are unclear about, we can always please bring to the table. We can always discuss. And yeah, and definitely there are many things which we should discuss, because I don't think by listening to this once and then by just following through this lesson you will understand every single aspect of the lessons. Okay, now we have exercise 1 here, so exercise 5.2. So they ask you to identify the bonds broken and the bonds formed. Okay, so of course the bonds broken in this case is actually, number one is the BrCl sigma bond, and then the CC pi bond. Okay, I must be explicit here. There's only one of the pi bond that's broken. Sorry, and then the bond that is formed is actually the CBr bond over here. Okay, yeah. So these are the bonds broken and the bonds formed. And then the next thing they wanted you to do is identify the electrophile and nucleophile. So again, the electrophile is actually BrCl. Why is it BrCl? Because if you look at the difference in electronegativity of Br and Cl, right? Br takes on a partial positive charge. Cl takes on a partial negative charge. So we call bromine center electron deficient or electrophilic. Yeah, but the whole species we call it the electrophile. Okay. Okay, remember this. When we say that something is an electrophile, right, it doesn't mean every single part of it is an electrophile. So for an electrophile, there is always an electron deficient site. We call that electrophilic site. And then same case, for alkane, although we call it the nucleophile, right? Not the whole molecule is a nucleophile. So specifically speaking, it is the pi bond that is a nucleophile. Okay, so in this case, for electron pair movement, it is the pi bond that breaks and it forms a new bond with the Br. So the Br is the electron sink over here because it's delta plus, and then now the sigma bond breaks towards the Cl. Okay, and then that's why you get a Cl minus, and then you form a carbocation here. Why is it a carbocation? You can imagine that after the pi bond is being broken, right, you are left with something like this. Okay, and then you form a new bond with the Br, and then that's it. So the carbon here is a bit naked in that sense, because it already loses its one of the electrons. So therefore it becomes a carbocation with 6 electrons around it. Okay, yep, hope that's okay with you. And then after that, ask you to draw a possible mechanism for the reaction using curly arrow notation. So you notice that the bonds broken are actually ClCl, and then the bonds formed are actually CCl. Okay, so of course in this case, it's some form of homolytic cleavage. Okay, and of course this cleavage will now, the Cl being cleaved, one of the Cl being cleaved, or one of the Cl atom being generated, will then form a sigma bond with the carbon radical. Okay, so to give rise to this. Yeah, so that's how you should draw the mechanism. Okay, yeah. 5.3 is the most important objective, which I highlight to you earlier on, which is 11.1c. And I think I cannot overemphasize it, because a lot of your seniors also have issues with this even now. So, but as I said to you in the earlier part of the lesson, whether you talk about delocalization or electronic effect or steric effect, you will be better at discussing them when you are in year 2 after learning more organic chem topics. Yeah, because it is only after learning these topics that you have a sense of understanding, um, like what do they really mean when we say inductive effect or so-called or delocalization of electron densities. Okay, but here I will just give you a very short snapshot on what to expect, but definitely even after listening it 5 times, 6 times, I don't think you will understand everything. Yeah, because a lot of it has to be discussed using a context. Okay, now I wanted to emphasize that for electronic effect, right, usually we are dealing with how the presence of a certain group will affect the distribution of electron density around a chemical species and how it gives rise to its unique reactivity, okay, which could either be enhanced or diminished. It really depends. Yeah, so the enhancement of electron density, we usually say that that there is the presence of an electron donating group. Then the reduction in reactivity, we say that usually there's a reduction in electron density, so we will usually say that there is the presence of electron withdrawing groups. Okay, inductive effect is a term which you need to be familiar with. Usually, it gives rise by virtue of difference in electronegativity values. Okay, so usually it is the presence of OH or Cl or NH2. Yeah, so usually for inductive effect, right, it might be better to say that it is what we call a sigma effect. Okay, uh, uh, or a sigma bond effect through the sigma bonding framework. What exactly is a sigma bonding framework? Meaning the whole skeletal structure involving sigma bonds. Yeah, but inductive effect usually is not, it cannot be induced over a long distance. So usually if let's say there's OH here, right? The inductive effect is mostly felt at this carbon, a little bit by this carbon, but this carbon, the third carbon, I would say, is almost as good as not present. Yeah. Okay. So I think I mentioned over here. So it's usually through the sigma bonding framework, and as you go further, its effect is more and more minimized. Okay. Yeah. So we call all this like Cl or NH2. We call them inductively withdrawing. So which means because of the inductive withdrawing effect, right, they will create, I mean, or rather the outcome is a partial positive charge at the carbon bonded to directly to it. Okay. Sometimes there are groups what we call inductively donating, and these groups are usually R groups, LQ groups. So LQ groups are what we call inductively donating, and the donating effect is actually not in the H2 curriculum. Is one part of the effect is known as hyperconjugation, but this is not in the H2 curriculum. So in that case, I wouldn't want to discuss too much about it. Okay, or we can discuss it more in our tutorials. Yeah, so the inductive donating effect largely is because of the presence of LQ groups, and particularly it is due to the presence of the CH group in those, or rather the CH bond in those LQ groups. But again, I will not attempt to go into details at this stage. Okay, yeah. And then there's also another effect known as the delocalization effect, which maybe I wouldn't call it an effect at this stage, but what I can share, okay, what I can share would be, let's say you have this butadiene, okay, if you try to so-called localize the CC double bond. So for example, let's say carbon 1, 2, 3, and 4, right? So this 1, 2, 3, and 4, right? So if you try to say that carbon 1 and 2 actually forms this pi bond, okay, side-on overlap, and then carbon 3 and 4 form this side-on overlap, right? But why can't carbon 2 and 3 also have an overlap like this? Yeah, if they are parallel, that is. Because sometimes your double bond, right, can rotate in such a way that they are not parallel. So for example, they can rotate until they are not parallel. Yeah, so in that case, there will not be overlap like this. Let's say this is projecting inwards. Yeah, then in that case, because the carbon 2 and 3 are not orthogonal to each other, so there won't be a continuous overlap of the pi electron cloud. In that case, there will not be delocalization. But let's say if they are parallel, then I would expect a delocalization to occur between them. Yeah, so this continuous overlap of p orbital, right? We call this we just say that the pi electron cloud delocalized across the 4 carbons. Yeah, so it's actually what we call a pi effect. If you want to be explicit, it's a pi effect. Yeah, and you might also be interested to know that pi effect is actually more prominent than inductive effect, because the pi effect actually involves electron density, right, being spread out over the pi framework, and this spreading out has an important implication on the electron density of the group as a whole. Yeah, so if you just want a very short snapshot summary, I would say that in most cases, the pi effect has a stronger and more domineering effect than the inductive effect. So if the two effects are at odds with each other, then usually the pi effect will dominate. Okay, so let me just emphasize this again. If the two effects are at odds with each other, right, usually the pi effect dominates. Yeah. You might be wondering, how is that possible for the pi effect to be at odds, right? Okay, so I will just give you this little example which you will learn in JC2, and then you will see why. Okay, so for benzene ring, right? For example, in the benzene ring, okay, you have the 6p or rather 6 carbon having an unhybridized p orbital where they form a continuous overlap of electron densities. Yeah, so that's why we say that the 6 pi electrons in a benzene ring are delocalized. Okay, now if an OH is bonded to a benzene ring, right? Okay, something interesting will happen because the OH, one of the lone pairs is actually or will actually be parallel to the pi electron cloud in the benzene. Yeah, so this lone pair can overlap partially with the pi electron cloud. Yeah, so this result in what we call the delocalization effect. So we say that the lone pair of electron on O delocalized into the phenol ring. So this is a pi effect. However, right, if you recall what we said earlier on, you will realize that, but my OH group is inductively withdrawing. Oh, yes. So you're right. So it is inductively withdrawing. So in this case, can you see that the pi effect and the inductive effect oppose each other? So OH is inductively withdrawing, so it will withdraw electron density from the sigma bonding framework towards the O, but at the same time the lone pair delocalize. So in then, which effect wins? The pi effect wins. So on the whole, if you look at the effect of the group on the nature of phenol ring, right, on their reactivity, that is, you'll realize that the OH as a whole, it is an electron donating group as opposed to it being electron withdrawing. Yeah, but this is only the case if it is bonded directly to a pi system. If it is not bonded to a pi system, then I don't think we need to even talk about the pi effect. Okay, because it's not even present. Okay, I know it sounds a bit confusing. I mean, I'm quite sure, but yeah, but that's the thing I want to emphasize, or that's the point I try to say at the start. Organic chemistry is, I think, the idea of delocalization, inductive effect, all this, or the electronic versus steric effect, all this. The reason why they are complicated is really because you really need a context to talk about them, and you need the presence of a functional group in order to fully understand what they are talking about, or what we are talking about, or how this uh, effect arises lah. Yeah, so in that case, really you will improve as we go by. Okay, yeah. So we have the inductive effect versus the delocalization. I avoid using the word resonance, which I will explain maybe a little bit in the tutorial. But do take note that inductive and delocalization, these effect, right? They are not events. Okay, so they are present in the system by virtue of some properties they have. Okay, so it is important to recognize the difference between the two as you journey through your organic chem. Okay, there's also another effect known as steric, but steric is usually easier to understand by students. Usually steric effect is regarding the crowding of the groups around a central atom. So if it's more crowded, then it's more difficult for the reactant to approach each other, and then it will give rise to either a slower reaction or the reaction might not even occur. So the steric effect sometimes we call it steric hindrance, because the presence of the crowded group prevents the reaction from taking place. Yeah. So for example, let's say you want a nucleophile to directly replace an X. If I have small groups here, it's okay, but if I have big groups, then it does not have an incentive to approach the electron deficient carbon, although the carbon is indeed electron deficient. Yeah. So yeah, that's probably how you want to interpret the steric effect. Yeah, usually there's a joke in organic chem is that if you cannot explain something via steric effect, then usually the electronic effect is something you can use to explain. Yeah, so most of the phenomenon you can explain by either steric or electronic. But in all honesty, if you look at steric effect, it is also due to repulsion of electron clouds. So actually steric effect is electronic in origin as well. Okay, electronic in origin means that the reasons why steric effect exists is because of repulsion between electron cloud and not attractions. Okay. Yep. Okay, so we're going to look at, okay, so the bigger the group, then the larger the group, therefore the more prominent is the effect, and it's something which you might need to highlight as well. I mean, in case you're answering any questions related. Okay, so next we have exercise 5.3. We're going to look at A first. So identify the inductively withdrawing group. So of course, definitely not too difficult. I mean, OH group is inductively withdrawing. Okay, and then over here, if you just put a delta minus delta plus, so the poor carbon here is flanked by two electronegative elements. So therefore, the two groups that are withdrawing are the O and the Cl. Okay, so it will make the carbonyl carbon, this is known as the carbonyl carbon, highly electron deficient. So it will be highly susceptible to nucleophilic attack. Okay, so that's usually the term we use in H2. Yeah, so whether delocalization occurs, so in this case, there's only one pi bond and it is a isolated one, so there's no delocalization. Okay, in our case here, there will be delocalization provided the p orbitals are parallel to each other. Okay, so that means that if let's say I have a carbonyl group with the oxygen overlapping like this, and then the CC double bond, if it managed to be in parallel, So yep, so delocalization will take place. But if I just do a small bond rotation over here, just do a 90 degrees bond rotation, then there will not be delocalization. Okay, the reason why there won't be delocalization is because after the bond rotation, right, my p orbital becomes orthogonal, yeah, to this. So they are like 90 degrees. So if I put my eyes here, then it will look like this, and then in front, there's another carbon in front. Okay, it will be like this. Yeah, so you notice that these two are orthogonal. Okay, yeah, so there is a condition you need to satisfy. That means that the 4 carbons, 1, 2, 3, or rather 3 carbon and oxygen, right? They must be, the p orbital must align, must be parallel to each other for you to have delocalization. Okay, and then for the case of this, there's no delocalization because there is a CH2 in between. Yeah, so for you to have delocalization, you need to ensure that there is no break in the conjugation. So meaning that there is no break in the alternating double and single bond. So once there is a break, then I will not have delocalization. Okay, so because the reason is once I have this, then this p orbital and this p orbital overlaps, but then I have a sp2 hybridized carbon over here. Okay, then and then I'm going to have another break like this. So you notice that um, these two pi system, right, become sort of isolated from each other because I have the middle CH2 group, which in the words of organic chemistry, we say that it breaks the conjugation. Okay, so this group breaks the conjugation. Yep. Okay, so there won't be continuous overlap. So no delocalization. So delocalization only occur in B2 provided, as I said again, you need to emphasize, provided that the 3 carbon and the oxygen have their p orbital aligned or parallel to each other. Okay? Yep. Okay. Now let us move on to the practical aspect of organic chemistry. Okay, so again, I will not spend too much time on this because the main thing here is you need to go through the practical in order to have a good experience to know what to do. Okay, so maybe just let me emphasize that for organic chemistry, you shouldn't be heating the organic compounds in the naked Bunsen flame because it's very dangerous. Okay, and if you are required to do distinguishing test, you are not supposed to have complicated setup, which means if your distinguishing test involve any form of reflux or distillation, then it's incorrect. Okay, so remember this. So organic distinguishing test, you do it in test tube. If you need to warm it, you do it in a water bath. You shouldn't be heating under the naked flame, or there shouldn't be any reflux. Okay, so we will tackle this in the practical rather than over here. I think that makes a lot more sense. Okay, yep. Okay, I'm going to move on to the synthesis parts, which I guess usually students will find a little bit challenging. I mean, in terms of doing the question, but then we're not working on a question now. Okay, we're not like how to synthesize a certain organic molecules because without learning a lot of reactions, you can't be synthesizing it. But I'm just going to introduce you a technique known as reflux. Okay, so what exactly is reflux? So without even referring to this diagram, I will use a YouTube video to showcase to you what exactly is a reflux. Okay, so first of all, right, this is known as a heating mantle. So you realize that a heating mantle allows the round bottom flask over here to sit very nicely into it so that it can then experience heating throughout. And usually, why do we use a round bottom flask instead of like a conical flask? It's really to allow even heating, okay, for your organic reactants. Okay. Yeah. Yeah, okay, sorry. So this is called a reflux condenser. So you realize that over here, right, it allows the water to flow in. So usually water flow in, the coldest water will flow in below, so that whatever liquid that gets vaporized, right, will be condensed back into the solution. Okay, so this is really known as reflux lah. Then you realize that this portion, it goes raw and raw inside. Yeah, so it's actually separated from the reaction mixture. Okay. Okay, then after that, he will adjust the flow of the water. Okay, so I'm just going to fast forward. Okay, so he put in the liquid, the solution to be reflux. Okay, if you heard what he said, the setup must be vertical. It shouldn't be tilted, so that it allows um, the condenser to perform its role properly lah. And then once you heat up, then your volatile liquid, usually it's a solvent, will start to evaporate. And then once it touches this portion, then it will start to condense back. So what exactly is reflux? So reflux is really you're trying to recycle the solvents because you don't want to keep adding the volatile solvent. So reflux usually begins when the condensation takes place. So which I'm going to show you very soon. You can see that the water actually flows through here. So if you see the tubing, it actually comes from the top. Okay, so this water tap actually goes in at the bottom. Okay, so you can see that they just fast forward. Okay, so this thing is boiling, and then you see the solvent actually drips back. Yeah, so this is known as reflux. So normally we start timing when the first bit of liquid starts to drip back. So let's say if they ask you to reflux for 15 minutes, you do not start timing when you set up everything. You start timing when reflux takes place. Okay. Okay, so this is when reflux takes place. Yeah. Yeah. So many a times students don't really understand what reflux is. So I hope that video, or you can just easily Google any of the YouTube videos, will showcase to you what reflux really means. Okay, so I encourage you to go and find out. Next year we'll have one experiment to let you try as a group on reflux. Okay, so this is a simplified 2D diagram. So if you wish to, you might want to learn how to draw it. You need anti-bumping granules. I think just now it wasn't added, or it probably has been added, but we didn't get to see, or magnetic stirring bar, in order to prevent bumping. Okay, yep. So remember, no Bunsen flame. Okay. Yep. Okay, so the separation technique, usually you use a Buchner funnel. So you connect this portion to a vacuum, so it's like a filtration, but it's a lot faster because of the pressure difference. So the liquid will flow through, will get dry up, or will flow through at a faster rate, and then your organic compound will be here. Okay, so again we'll do it in JC2. You get to do one of the experiments in JC2 lah. Yeah, together with the reflux. Okay, so abstraction. So abstraction, usually we will use a separatory funnel for abstraction. Okay, so again, we will try this experiment or similar experiment in JC2, but usually a separatory funnel, right, allows the denser liquid. So there will be two liquids, one denser than the other, and then they do not mix. So there will be two layers here. So this is the less dense layer, usually is the organic layer, and the denser layer is the inorganic layer, or the water or the aqueous layer. So usually after you shake it you shake through the separating funnel, right? Then you need to leave it for a while for the two liquids to separate. So once they separate, then you can release one liquid off, or rather you can drain one of the solution off, which I'm going to show you in another YouTube video. How to use a separatory funnel. These funnels are useful in separating two or more divisible liquids. Liquids and seconds of a keep the funnel extensive. It is important to use a funnel that provides the line of finding of solutions in the thread and the extraction solvent. When adding the liquids, place the true to the stop pockets in the closed position. Add the solutions be extracted first, followed by the extracted solvent. Stopping the funnel and holding the stopper in place, then invert its. Okay, so I just elaborate a little bit. You can see that now there are two layers, right? So if you heard what he said just now, you add in the solution, right, with things you want to separate out. So meaning, let's say this for the first solution he poured in, right, maybe it contains some organic compounds which he wanted. Yeah, but it could be after a reaction or whatsoever. And then he might find out from another earlier example that he can use a non-polar solvent to actually extract out the organic, the non-polar organic molecules that is kind of like partially dissolved in water, like something like that. So when he pour it in, you can see that now there are two layers. So later on he's going to shake it, right? So after he shake it, then you will realize that the organic molecules, if they tend to be more soluble in the non-polar solvent, will actually, I mean, dissolve in it, but because this particular example is non-colored, I mean, it's colorless, so you can't really see the difference. So here he's only demonstrating to you how exactly you should be using the separatory funnel. You need to release the built-up pressure. The reason is because organic compounds tend to be highly volatile after you shake it. Yeah, so the releasing of pressure is highly necessary to prevent any mishap. Close the stop and continue to swirl. Open the stop again to release pressure. Repeat these steps several times. When the liquids have been adequately mixed, place the funnel back in the mixture and stop. Wait until the separate. Open the stop. You can see that now there are two layers, but because it's colorless, so you can't really see it very clearly, but obviously there are two layers. So he will open this, when he turn on the tap, right, the bottom liquid will be drained off. Yeah, so that's about it. That's how I use the separatory funnel. We may or may not be able to give you that particular lab experience, but for those of you who have done research before or who are doing related research now, you will know what a separatory funnel is. Then maybe you can share a relevant experience with your friends. Okay, yep. Okay, so these are procedure which you need to know for planning. So I think it's good to maybe understand it a little bit. Usually for compounds which you have gotten from the organic layer, they tend to be wet, a little bit wet. So you need a drying agent, such as magnesium sulfate or calcium chloride, to be added to the organic to the organic solvent containing the organic compound you wanted, so as to dry it. And then you notice that once it's more dry, right, your organic solvent, right, there will be less cloudy. Okay, you'll kind of like clears up. I think you really need to see it to understand what exactly is going on here. Although I can try to explain it. Yeah. Okay. Yeah. For liquids, you can use distillation for separation. Sometimes it can be easier. So you can either use simple distillation or fractional distillation. Yeah, so I don't think I need to go into details here. You can either use an oil bath or water bath, or you can use a heating method. So it's really up to you. Recrystallization is often used to actually separate a solid out. Yeah, so again, we will get to do it maybe in year two, in the same practical we are talking about. So usually you try to dissolve the crude compound in a minimum amount of hot solvent, okay, until it reach super saturated solution, and then after you cool it down slowly in order for the crystal to appear slowly. So usually, I mean, the crude product could be like powdery like, but the actual crystal could be like needle shape or some very beautiful crystal like shape. Okay, so after you let it cool down, crystallize it out, etc., then you will need to test for its purity. Yeah, so this is known as recrystallization. So it's a technique that you only get to do it usually in research. Yeah, but I think in JC2, where possible, we'll try to give you the experience. Yeah. Okay, and usually they are being stored in a desiccator to dry. Yeah, so a desiccator usually over here, it contains drying agents. Yeah, okay. Okay, so we have a exercise 6.1 over here. So they ask you to refer to the reflux setup in figure 19. Okay, so I think this is the particular reflux setup which we were talking about just now, which I show you how to go about understanding it through the video. So over here they ask you some questions. I think some of them I have already answered. Like, what is the purpose of adding the anti-bumping granules? As I said, is to prevent the sudden difference in pressure being developed in the liquid. Yeah, so that's usually called bumping, which could be very dangerous. So is to help the solution to boil evenly. Okay, then what's the advantage of using a magnetic stirrer instead of the anti-bumping granules? Okay, so if you use a magnetic stirrer, right, which involve a magnetic stirring bar, you can easily remove the magnetic stirring bar. But if you have anti-bumping granules, right, they will still stay around as solid. So it could be a bit hard to remove, and especially in the purification stage. You don't want them to affect the purity of your compound. Yeah, and then why should the condenser not be stoppered? So you want the pressure to be at atmospheric pressure. So you don't want the pressure to build up inside because you are involved heating and it's actually quite dangerous. Okay, then for the general procedure for recryst, answer the following question. The purpose of the hot solvent, right, is to allow the compounds to be dissolved, more of the compound to be dissolved at a higher temperature. Okay, and then to actually produce the so-called super saturated solution, which means if you elevate the temperature to, let's say, 80 to 90 degrees Celsius, and then more of it can be dissolved, so that after you slowly cool it down to room temperature, right, then your compound hopefully will have time to crystallize out nicely. So we call this recrystallize out nicely, so that you can get the nice crystals. Okay, so in order for you to get a nice crystal, then you need to give it some time. Yeah, so that usually the impurity will not tend to crystallize around the nice crystals. They will tend to be separated slowly. Yeah, because I think in terms of thermodynamics, when the solid starts to form out in a nice way, then you will want to attract those with similar species. You attract those similar species. So let's say you are crystallizing out maybe paracetamol, for example. Then slowly when the solid starts to build up in the crystal lattice, right, it will attract paracetamol molecules instead of other impurities. But you have to do it slowly in order for you to achieve the good effects. Okay, why only minimum solvent? Really, if you have too much solvent, then you're going to lose some of the compounds into the aqueous, or rather into the you're risking some of the compounds dissolving in the solvents. So you're not going to get maximum amount of crystal, or to the best of your ability, you're not getting the maximum amount of crystal when the solution cools. Okay, then why is cold solvent necessary to wash? Imagine you use hot solvent, they're going to dissolve it back, right? Yeah, so definitely you need to use cold solvent. Yeah, so try to cool it in the ice bath before you use it. Okay, normally when you check the purity of your unknown, right, you will use what I call a melting point test. Okay, I'm going to showcase to you the melting point apparatus in this video, so you can take a look. So it looks something like this. So it looks something like that. So there's a reading here which you can read off the temperature. Yep. Okay, so yeah, so they are going to use this particular sample which melts at about 80 plus degrees Celsius. Okay, then okay, so they are going to use a capillary tube to actually introduce some of the powder into the capillary tube. Okay, so okay, I have skipped some parts because I don't think they are necessary. So if you are interested, you can read about it. Basically, what they did, what he did earlier on was he need to set up a temperature gradient. So the temperature gradient will sort of decide like for every 1 minute, right, what's the increase in temperature. So because earlier on we saw that the fluorinone actually melts at about 80 degrees Celsius, right? So you will start to heat from 70 degrees Celsius. Maybe at every 1 degree Celsius, I mean the gradient is about 1 degree Celsius per minute, so that you can check carefully when it has melted. Yeah. Okay. So so you notice that he's putting the capillary tube in here and then he's observing it from the top. Okay, so there's a microscope here. So he'll be able to see whether it melts. Okay, so you can see that this thing, right, has not melted yet, so it appears solid. So how do you know it has melted? You will see that the solid starts to collapse. Okay, so we'll take a look. Okay, but anyway, you don't have to keep staring at it. Just stare at it when it's near the perceived melting point. You might be interested to know what is the plateau like. Okay, so as I said to you just now, remember just now at the start it was about 24 degrees Celsius, right? So it will heat very quickly to about 71 degrees Celsius, where it will then heat up slowly until you reach the melting point. How do you know whether the melting point has been reached? You wouldn't know. So usually you set it, maybe let's say the melting point, perceived melting point is about 80 degrees Celsius. You will set it until like let's say 90 degrees Celsius, and then you will set the parameters like every increased temperature 1 degree Celsius every 1 minute. Yeah, so that you can clearly denote or determine the melting point. Okay, so he set it to be 2 degrees per minute lah. Yeah, earlier on I said 1 degree, but again it's really up to you. Okay, 2 degrees might be faster, yeah, but less accurate. Okay, can you see? Yeah, can you see that the solid already melted? Maybe I show it again. Yeah, you see here slowly, yes, it starts to melt. Yeah, so usually you will record a range lah. But you notice that just now, right, he ramped it at about 2 degrees Celsius per minute. So actually that's too fast lah. So if you do it at 1 degree Celsius per minute, then your melting point range will be narrower. So the narrower it is, the better is your experiment. Because why are we testing the melting point? Because we want to see how accurate is our experiment. So or rather how pure is our compound lah. So if we indeed make that particular organic compound, then you would expect it to melt at that particular temperature. So in this case, the compound he used was fluorinone, right? So reported melting point is about 82 degrees Celsius. So you expect it to be around that range. So I think in your notes it's written that your pure organic solid must melt at a sharp temperature. So usually that's, I mean, plus minus one degree Celsius from the reported melting point. Okay, so I guess that's the end of topic 8. I hope you find the whatever has been shared educational, and do look out for the next topic which will be out very soon.